So, our last and final presentation, we'll have an introduction and what Rust borrowed from
Thank you.
functional languages by Emil.
Thank you very much.
Yes, I will get you the little back. Joachim, you have to come back with the
HDMI adapter.
No, the adapter. No. Yeah.
There's always something with this video links.
Yeah. So, welcome up on stage, and I'll leave it to you.
Thank you very much. Okay, so I'm here to speak about what Rust borrowed. So, before we begin, briefly about myself. I'm Emil. I'm an engineer at Amazon Web Services. I've been working primarily in Rust for the past 2 years, since the fall of 2018, initially at Imperva, and as of this fall at AWS. I was delighted when I got to AWS to see the extent that we're already using Rust internally. I also like flags for some odd reason. I'm not sure how that actually happened. Here's my favorite flag. This is Kamchatka Oblast in Russia. Let's just take a moment to appreciate that flag. Yeah, all right. So, in this talk, Rust is a very neat, highly hyped systems programming language. So what has systems programming got to do with functional programming? Aren't those at opposite ends of the programming language continuum? Well, not exactly. I probably don't need to tell this audience that there's a lot of great ideas in functional programming, and a lot of those have been creeping into the mainstream over the past 10, 20 years. Rust takes this further than most languages, though, to the point where I sometimes think of it as the unholy love child of C and Haskell. I'm going to take you through a worked example with an emphasis on the functional elements in Rust, in an attempt to convince you that Rust is a good language for functional programmers. The example as such is pretty involved. The point of it is not necessarily that you need to get all of this particular example. It's a bit flimsy and mostly there to demonstrate a bunch of features. To assist me, I've got grumpy Joe McCarthy of Lisp fame. He's normally a nice guy, but is a bit ill-tempered today. Might be because he's been dead for 9 years and I brought him back for a lousy talk about Rust. So before we dive in, let's speak about what functional programming means in a highly subjective way. I believe that the core of it is that your go-to for how you structure things is around composing functions, much like our earlier speakers mentioned. And that you work mostly with immutable data that is successively transformed in the flow of your program. You usually get to model your data using something like algebraic data types. You benefit from a reasonably powerful type system, usually with type inference and powerful generic support. Although, of course, there are dynamic functional programming languages, as we've seen. Admittedly, this isn't a very complete definition of functional programming, though. In fact, I largely picked it to suit my agenda. What are some salient details about Rust then? Well, first off, it has first-class functions. It has algebraic data types. It encourages immutability. In fact, the borrow checker in Rust sometimes forces you to it. And finally, it has a really nice and powerful type system. The borrow checker in particular has certain implications that drives us towards functional thinking. The fact that you can't in Rust have mutable access to something in multiple different locations kind of encourages a functional way of thinking about things. So let's say we want to draw some flags, as one does. It's of course not the case that all flags consist of simple rectangular geometry. Looking at you, Nepal, and Ohio. But nonetheless, a lot of flags can be drawn using simple rectangles. So let's explore that for a bit. Don't worry, Joe, it will be fun. Of the functional programming languages that are just now entering the mainstream, the one that has got me the most excited is probably some types. For people unfamiliar with the concept, a sum type is essentially an enum, or a tagged union, that can hold data. It's not a hugely useful concept in its own right, but coupled with pattern matching, it's a killer. In this particular example, we have a simple data type called shape, with a variant circle and rectangle. And the key takeaway here is that circle has an integer parameter corresponding to the radius, while the rectangle variant has two integer parameters corresponding to width and height. And here's pattern matching. Key well-known feature to Haskell developers, and also available in some form in most functional programming languages. In Rust, we do this using the match statement. So I enumerate my variants, circle and rectangle, specify the variables I want to bind these to. And this is really nice because it allows me to handle these variants in a completely safe way. The language actively prevents me from misinterpreting my data. So we can split flags up recursively into a tree structure of one-colored strips. Splits can be either horizontal or vertical. We arbitrarily subdivide each such strip at a point, a pivot point, the third parameter in this horizontal and vertical. And we kind of pick by convention that we'll divide this into parts of 100. So generally, I think this snippet is probably straightforward. The one odd thing here for non-Rust users may be this concept of box, which just means that these parameters are going to be heap allocated, which is required since the size of a recursive type can't be calculated if it contains itself. Yeah, that's true, Joe. Let's think about what this would look like in Java. The key thing about the alternative approaches, the conventional approaches, that it leaves more room to error. In this, we would have to have fields for each of these different things that goes into the enum, and that leaves us with the possibility of having invalid states. What does it mean if we have a horizontal strip that only has one child rather than two? We could deal with that, but we would have to add extra conditional logic to our program, so it makes it less clean and more error prone. So in order to draw a flag, we'll descend the geometry tree and subdivide the drawing area as we go. To make it easier for callers, because of course we want a nice API design around our flag drawing library. There is a small convenience method. So the consumers of this API call the draw function, which delegates to the draw area, feeding it the starting x and y coordinates and the full width and height of the drawing area. This impl block right here is how we define methods in Rust, how we attach a function to a struct or an enum. The first thing we do is that we in this draw area method is that we deconstruct self, which is one of these flag geometry enums, and we handle the case of solids, which is an area of one particular color. And all we have to do here is that we visit every single pixel and set it to the color of that particular geometry. We handle the horizontal and vertical strips by subdividing the input coordinate and the input dimensions according to the specification. Calculate the width based on the pivot and the input width. For the first parameter, for the second parameter, we just offset it by that. The code for the vertical variant is fully analogous to this, so we don't need to go into that in detail. Yeah, definitely. Some types and pattern matching make this type of thing really convenient. Notice that we didn't keep any state except for our drawing buffer. And now we try it. We can construct some geometry by hand by nesting flag geometry calls. And then we run our code. Vive la France. That way of constructing flag geometry wasn't great, though. Right you are, Joe. Right you are. We need the DSL. Introducing the flag definition language. Our language is, of course, based on S expressions. It includes 3 functions. S for a solid area, V for vertical splits, and H for horizontal splits. So how do we define this in Rust? Well, we use a sum type, of course. In this case, we only need 2 variants. A list, which is just a vector over other S expressions, and a literal, which is some specific string. To make it easier later on, we'll define some helper methods for retrieving a list and literal. Both of these works only for one of the variants. And a safe Rust doesn't have a concept of null. We'll need to use the option type. The option type is these days widespread enough that even Java has it. In Rust, it's an enum with the variants sum, that takes a single value, and none, which doesn't take any value. Exactly as in Haskell, as it happens. Our parser takes an iterator as a parameter. In this case, a special version of an iterator that allows us to peek 1 character ahead. It inspects all chars, matching them as it goes. The peek and next method both returns an option of a value. As long as it returns sum, there is more data to be read. We don't need to understand all the details of this parser, but a few things are worth pointing out. The first is that we only need a single state value, because an option over our S expression enum is rich enough to represent all the parser states. For instance, these non-branches are hit when coming in fresh, and haven't yet decided whether to parse a list or literal. Then there are the two cases that handles list building. The key is that we can recurse whenever we need to create a new nested S expression. In that way, we can keep our local state very simple and only need to manipulate state locally. Finally, there are two cases for handling literals. All in all, a reasonably compact little parser. I code golfed this a bit to get it to fit on the slide. And a combination of sum types, pattern matching, and recursion really simplified things a great deal compared to the imperative style. The remaining thing is that we need to transform our S expressions, or the tree of S expressions, into a flag geometry tree, the original enum that we introduce for drawing. We'll of course do this recursively as well. Rust also supports something called slice patterns, so we can match for lists of certain sizes. Here we look for solid blocks of a single color, that is sequences of two instructions, where the first is the literal S. We only have one other case to handle here, for vertical and horizontal blocks. Those S expressions has 4 parameters that we need to deconstruct. The question mark operator that we see in some places here are for error handling and unpacks an option for us, short-circuiting the function call and returning none if it ever encounters a missing value. So it makes error handling very convenient. Throughout this presentation, I'm using option everywhere. In a real-world program, you would probably be using result instead, which allows you to provide more context about failures. The error handling experience is still much the same though. Now we just have to tie all of this together. We'll pass the flag definition language through a command line argument. The args function here returns an iterator on which we can call the env method to fetch the first argument. That method actually returns an option of a string. And our S expression parse method and toFlag geometry method also returns options, so we can just chain them together. Rust doesn't have proper monads, but a lot of things follows a monadic pattern where you can chain them together like this. In addition to option, there is result, which is like Haskell's either iterators as a flat map method. And in asynchronous Rust, futures also has an and then method, and so forth. This pattern helps simplify control flow greatly, but without proper monads, you can't abstract over monadic types, so you currently can't write a function that operates on either an option or a result, for instance. All right, so now we can try our FDL parser. And it works. I know, that's one great flag. One of the things that we glossed over earlier was around how we handle colors. In our parser, this is where we turn our single letter color code into our color type. But how does this actually work? Parse is a standard method on the string type. This is the definition. Notably, this function takes a generic parameter f with the requirement that f must implement the from trait. What's a trait? Yeah, that's a good question. At first glance, a trait is like a Java interface. Here we implement the standard from trait on our color type, and based on that we can magically parse strings into colors. Oftentimes, as in our case earlier, Rust can just infer the desired type. But traits are actually much more powerful than interfaces. For instance, say that we want to abstract the drawing library. We'll define a new trait, MS Paint, which defines a way of retrieving the dimensions of the image buffer, as well as a way of drawing a rectangle. And we can now implement that trait over a RGB image type from our image library. That's something you can't do with OOP-style interfaces. You can't define and implement your own interface on somebody else's type. Well, maybe in Golang. As a side note, we handle the name clash of width and height here by directly passing self as a parameter to the methods on RGB image. This lays bare what you may have suspected, which is that Rust methods are really only functions with some syntactic sugar, much like Python, really. So now we can make our flag geometry independent of a drawing library by just abstracting over MS Paint, saying that any P that happens to be MS Paint will do. Yeah, you may have seen this elsewhere, Joe. Rust traits are pretty much Haskell type classes. The heritage is clear. For instance, consider that equality is handled by the EQ trait in Rust and the EQ type class in Haskell. And ordering, essentially Java's comparable, is handled by ord in both languages. But Rust finally decided to make a strong statement of independence and decided to name the string formatting trait display rather than show. Take that, Haskell. All right, so where do we go from here? Denmark, apparently. Say we want to draw a Nordic flag. It's rectangular enough, so that's good. But we end up having to repeat the exact same definition for the upper and lower part of the flag. Wouldn't it be nice if we could add some type of reference so we can avoid that repetition? Yeah, that's what the DSLs are for, right? So here I've introduced T for tag function and R for reference function, so we can eliminate that repetition. So how, thinking about it, would we implement that? It's not conceptually very hard. We just need to resolve the reference in some way. We could extend our flag geometry enum with 2 new variants and resolve it as we draw. But that would make drawing stateful and more significantly fallible. We could add another function for resolving a geometry tree, but if we accidentally draw something without resolving it first, the drawing would still fail. And resolving references during parsing is also messy. In the end, we always want to strive to make invalid states unrepresentable, especially in the critical phase of the program. Remember, kids, fail early, fail fast. So our original flag geometry enum remains unchanged. We introduced this new enum, which has a tag and reference variant, and also the methods needed to perform the transformation. And then we just need to add another step to our parser chain, and it all neatly comes together. Yeah, agreed. Java's optional type supports the same type of combinator, and Java's stream API is much like Rust's iterator. So this style of programming is by no means unique to Rust, but it's arguably nicer and more natural combined with some types and traits, and certainly more typical of idiomatic Rust than of idiomatic Java. All right, so to summarize, Rust might, at first sight, look much like a C derivative, but in practice it draws a lot on various functional programming languages like Haskell and OCaml. In fact, the original Rust compiler was implemented in OCaml. Hence, it follows naturally that it's oftentimes beneficial with a functional approach. Even if you happen to prefer an imperative style within your functions, you can organize your program according to a functional philosophy. Functions can be pure and small, which makes your program easier to reason about and easier to test. Abstractions can be based on function level polymorphism and parametric polymorphism. While Rust does support OOP style trait objects with dynamic dispatch, it's generally not the go-to solution for most problems. And that's all I've got. Did we get any questions? Or maybe remarks?
No question or remark so far. However, I have a question.
Sure.
You referenced Haskell quite a lot. Have you ever programmed Haskell, or have you just...
A little bit, but I'm definitely not a very good Haskell programmer.
Did you, before you worked with Rust, where did you come from? Java, C++, or?
Well, my main background is in more classic languages, so I've kind of come to appreciate functional programming as it's leaped into the mainstream, and then I've been reading more and more about it as it's become an ever more relevant topic.
Yep. Thank you. Well,
thank you.
I don't see any further questions, so then I would like to... Yes.
Why did you pick S expressions for the DSL?
Yeah, why did you pick S expressions for the DSL?
Well, at the previous job of mine, we had a proud tradition to create bastardized Lisp dialects. I think we had 3 of them by the time I left. So I guess I have a bit of a tradition of doing ill to Lisp syntax. I apologize to you, Clojure guys.
No problem.
Thank you very much, Emil.
Thank you.
Very nice presentation. And thank you to everyone that watched Func Prog Sweden, the 5th and last for this year. So we'll come back next year. I'll do a planning with the other guys and we'll come back. And if you want to speak or present and get your presentation recorded and published on YouTube and live stream and become a YouTuber like the next generation will be, this is the place. So please contact me and we'll put you on stage. Thank you very much, everyone.